Hello, my name is Najah Farah. For my graduation project, I work on diagnosis and the classification of Alzheimer disease with machine learning models. Alzheimer is a progressive neurological disease that affects memory and cognitive function. Early diagnosis is essential to slow its progression and improve quality of life. The goal of my project was to build a system that could automatically classify brain MRI images into categories, indicating Alzheimer's severity using AI. I used a public available dataset from Kaggle, which contains MRI scans labeled as very mildly demanded, moderate demanded, and non-demanded. Now we are going down. This is my non-demanded picture. I took my dataset for direct. Also, this picture I took directly for my dataset. It's a moderate demanded. I apply both classical and deep learning models for future extraction. I use BCA and LDA for classification. I implemented support vector machines in the deep learning section. I built a CN model from scratch. I also use pre-trained models like FGG16 and efficient for transfer learning, which helped improve accuracy. And this code is a BCA code. And before training classical machine learning model, I use BCA to reduce the dimensionality of the data. The original MRI feature space was very large, so BCA helped me compress it while preserving K patterns. I found that using just 158 brain symbols component, I could explain 80% of total inference in the data. This made the model faster and more efficient with sacrificing much performance. And this one, it's a LDA. For LDA accuracy, I find 93% for testing data. Accuracy for training data accuracy, it's 100. And this one is resizing. I did resizing. This is printing. So doing printing. And SVM. For SVM, I tested support vector machine models with different kernel function. Linear. This one it's a linear. This one it's a poly, and this one it's a RBF. The linear SVM gave the best result. It gives best result, which 98.88 accuracy. Yeah, it's there. Also, this one I can show for the word I provide for in word. For linear, I find the accuracy there. It rate and precision 93.8, recall 98.67, and effort squared 89.99, and the ball every result, and you can see in there for directly. Now we are going back for our code. I also implemented FGG16 using transfer learning. It's well-known CNN pre-trained on ImageNet. I find it by removing the original classifier and adding my own layer for 4 Alzheimer categories. After training it for 10 epochs and critical MRI images, the model achieved 90.5 accuracy, which makes it one of the top performing models in this project. It also maintains low validation loss and high generalizations across the dataset. Also, I use the TensorFlow image data from directly to load and process MRI images. The dataset was divided into training and test set using 80-20 split. I then apply efficient netball, a powerful pre-trained model, to classify 4 stages of Alzheimer's disease. The model was training for 8 epochs and achieving high validation accuracy. The training, this one it's a total parameters and trainable parameters and non-trainable parameters. And this the training graph shows stable learning with consistent improvement invalidation performance, confirming the model's generalization ability. Also, one of the best performing deep learning models in my project was efficient network used with transfer learning. I used graphical MRI image resizing to 128 by 128 pixels and added a custom dense layer for class classification. After training the model for 10 epochs, it achieved an accuracy of 82.54 with validation accuracy of around 82.7%. The training the training graph showed that the model learned stably without overfitting and the loss decreased steadily. Efficient network was effective that identify Alzheimer's stage from the brain scans. I also experimented with increasing the image resolution to 224 times 224, which is more compatible with efficient network region design. The function of the model achieved an accuracy of around 80.86% on the test set, showing consistent validation performance and generalization. The training plot confirms that the model was stable across a bunch with no sign of overfitting. The test how well the model performed on new unseen data. I randomly select the test MRI images. The system makes a prediction and compares it to the actual diagnosis. In most cases like this one, like the last one, the model predicted very mild demand correctly. However, in this example, the model predicted very mild when it was actually moderate. Even though same errors exist, this demonstrates the model ability to generalize from training data to real samples.